So this one is probably one of the trickiest ones so far because it's going to require us to recall quite a few things that you maybe didn't see in your old high school geometry class. So what we have here is a triangle ABC. So ABC with both an inscribed circle, so that's this little circle inside that triangle that tangents each of the three sides, and we have a circumscribed circle about the triangle, so that's the large circle that passes through all three vertices of that triangle. And the only information that we're really given here is that the centers of those two circles are symmetric with respect to side AB. So what it means for 2 points to be symmetric with respect to a line is that that line is the perpendicular bisector of the line segment between those 2 points. So what we know here, so if I give these things some labels, so I'm going to call this O1 and I'm going to call this O2. So O1 is the center of my inscribed circle, O2 is the center of my circumscribed circle. So I know that AB is perpendicular to O1, A1, and I know that, let's give that point, let's call it M for midpoint. I know that O1M is equal to M O2, and so that's because 2 points are symmetric with respect to a line if that line is a perpendicular bisector of the line segment between them, between the 2 points. So that's a definition for what it means for 2 points to be symmetric with respect to a line. All right, so ultimately we're trying to find the measure of angle A, angle B, and angle C. So we're going to use some information that we know about inscribed circles and circumscribed circles. So a lot more with the inscribed circles here is what's going to be helpful. So the way we construct with a ruler and compass an inscribed circle is that the first thing we do is we find the angle bisectors. That last one's a little funky. So we find the angle bisectors of the three angles of the triangle, and the point where those intersect gives us the center of our inscribed circle. And then we draw perpendiculars from that point. I'm going to have to move this O2. We draw perpendiculars from that point to each of our sides. I've already got the one to M there. And that determines the radius of that inscribed circle. So I know, for instance, that all four of those segments are equal. So they're all equal to the radius of that inscribed circle. So I'm going to draw a couple more things here, and then make some equations that we can use. So I'm also going to draw another radius, or I should say a radius of my larger circle here. It might look like O2C is a radius of that larger circle, but it's not necessarily here. And then I'm going to extend that, actually, so that this is a diameter. Since that's a diameter, I'll call this point D. And I'm also going to draw this radius here in case I need it. And I'm going to draw a chord here. So let's give a few more things some labels here. I want to label this point and this point. I'm going to call those E and F. And I think that might be all the labels that I need here. Okay, so there's a few relationships that we want to establish. So I know I have right triangles here, correct? So we have a congruence theorem called the hypotenuse leg congruence. And so what that says is that if in two right triangles the hypotenuse is equal and one leg is equal, then I know that the two triangles are equal in measure. So certainly I know that O1F is equal to O1M because those are both radii of the in circle. So inscribed circle or in circle, same thing. And I know that O1B is equal to itself by reflexivity. Okay, so, and that is the hypotenuse of these two triangles. Let's see, I've got triangle O1BM and triangle O1BF. And so if we have congruent triangles, we know that all of their corresponding parts are equal. So in particular, I can say that angle O1BM is equal to angle O1BF, and I'm going to let that be called X. So that's this angle and this angle. And I also know that these are equal for a number of different reasons, right? So I could have used the fact that those are corresponding sides in those two congruent triangles. I can also use the fact that those are tangents to a circle tangents to a circle to the same external point B. So tangents to the same external point are always going to be equal. All right, so then I want to look at triangle O1MB and triangle O2MB. And what we can see there is not a hypotenuse leg congruence, but we have a side angle side congruence that gives us that triangle, what did I just say? O1BM is congruent to triangle MBO2. And so again, corresponding parts of congruent triangles are equal. I should write that here. This is an important statement. Corresponding parts of congruent triangles are equal. I make my regular geometry students memorize that mantra, so that's a very, very important statement there. And so again, I can say that angle O1BM is equal to angle MBO2, which again is equal to x. Cool. So now what else? Well, I can extend this over to the left-hand side. So again, I know that this is a right angle. I know that O2A is equal to O2B because they're both radii. Not 2Ds, not whatever that was. Oh no, I lost my circle. Come back. So those are both radii of our circumcircle. So those are equal. And now I can use my hypotenuse leg theorem, since those are right triangles, to say, again, that triangle, what did I call it here? MBO2 is congruent. It's not very good congruence. It's congruent to triangle MAO2. And again, we have corresponding parts of congruent triangles are equal. And so this angle is going to be x. I can do again a similar argument to show that all of those angles are going to have that same measure. So let's see if you can fill in the blanks there. So basically, I have that angle MAO2 is equal to angle MBO2, and I also get NaO1 and angle O1AE. And so those are all having angle measure x. Let me scoot this over here, actually. So a little bit of missing information to go from, to go from here to here. But hopefully you can follow those steps of hypotenuse leg congruences and side angle side congruences to get all those right triangles as being congruent. Okay, cool. So now, well, now let's use this point D that we have out here. So hopefully you would agree that DB is a diameter. And so therefore angle, what is that? Angle DCB is inscribed in a semicircle. And so therefore angle DCB is a right angle, right? So that's a right angle. Now, I want you to also notice that angle BDC is going to be equal to angle BAC because they're both inscribed angles with corresponding arc BC. Right? And, well, we also know that angle BAC is 2x, right? Because x plus x gives us 2x. Cool. So I know that angle BDC is equal to 2x. So that's going to be useful information. That's going to be useful information. And then in that same triangle, I can see that angle DBC is 3x. So we can use our triangle sum theorem that tells us that angle DCB plus angle BDC plus angle DBC should be 180, and I can substitute 90 degrees there, 2x there, 3x there. Combining like terms, we see that 5x is equal to 90 degrees, and if I divide 90 by 5, I get 18 degrees. And so now I can easily find the desired angles. So let's go back to our picture, and we're looking at triangle ABC, right? But let's be a little bit more precise about how we're naming these things. So I'm going to call angle A angle CAB, which we can see is equal to 2x. So angle CAB is equal to 2x, which is 36 degrees. So there's one of our desired results. Similarly, angle ABC is also 2x, and therefore 36 degrees. And so the only one we have left to find is angle ACB, and we'll get that by subtracting from 180. So angle ACB is going to be 180 minus 36 or 180 minus 72, and so we get that angle ACB is 108 degrees. Whew, quite a long one there.